Last time I talked a little bit about the Kadanoff blocking scheme, which is going to be implemented in the RG. And then I talked about the spin model based on the Ising model, which we distorted quite in a bad way to get a Gaussian theory. So I'll just summarize what we did. So we started with this. Well, I won't go over this, but we'll just mention we did this Kadanoff's idea. So remember his idea is the heart of the matter. The idea is to get a new Hamiltonian from an old Hamiltonian, where the new Hamiltonian is obtained by combining a small region of the old space. So there are 4 points here and make it into 1 point. So you change your length scale by a factor of 2 by combining some spins, in some sense, some kind of an averaging. And that averaging process resulted in some mapping from the parameter in that was just k prime is some function of k. So he invoked a mapping like this. And it was crucial that this is an analytic map. Why is it analytic? Because this process involves only a few spins. So when you have a finite number of degrees of freedom, things are going to be analytic. And he said this defines a map, and then you keep iterating this map. And he showed how the non-analyticity comes about. So you get some fixed point behavior where there's a fixed point which satisfies the property that it's fixed. And at this point, you find that the correlation length goes to infinity as some power of k minus kc, and you can get out the exponents. So this is the intuitive idea. And then we're going to implement this in some simple model. And we started with the Ising model, which has discrete spin up, spin down. And then we distorted it to basically a model involving, so here the action is some k Sn plus I sum over n. So these are the spins at neighboring sites in all directions. So the model is basically this partition function, sum over all, integral over all spins. Or I can, since it's a continuous variable, I can write sum over all spins. Put it here. And this was distorted to a model where we ended up with something like this, where the delta function is replaced by a Gaussian weight like that. And then this term is still there, plus the k. And so on. And as I said, there's a class of models where there's a Sm squared and an Sm4th term. And in some limit, when the coupling, when the coefficients go to infinity, it reduces to an Ising spin with a discrete number of states. So in general, there's some u. So when both u and b go to infinity, you get back the discrete spins. If this is finite, you get a simple model with Gaussian and quartic interactions. If you put u equal to 0, you get the simple Gaussian model, which is what we're going to do now. So in some sense, the model we're studying now, which is just this, is some limit in a class of models where the other end is the Ising model, and this end is this model. Okay? So that's just motivation for this model. But my main purpose in studying this model is to illustrate the techniques, the steps involved in the renormalization group scheme of Wilson. And then we will do a more complicated model where the algebra will be, the steps will be the same, the algebra will be a little more complicated. Okay? So this is what we're going to do now, and I'll just summarize the final steps.
So at this stage,
yeah.
There's no reason to just stop at the fourth power of spin.
No, you could keep going. Yeah. So then we'll argue later on that some powers are more important than others on purely on dimensional grounds. So that's the concept of relevant, irrelevant, and marginal variables. So what did we do? So I won't go through the algebra again, but we did some change of variables. First of all, we made this into a continuous variable over there. And then we went into momentum space. And we finally wrote down an action which was like this. So I'll just write down the action. So the action was this was the end result, where Q is the momentum integrated over. So it's Fourier conjugate to the position space. And if I'll just remind you that the sigma Q was defined as where Sn are these spins. Okay. And then we also approximated Q. So this is in units of the lattice spacing. So the lattice spacing is, if you want, you can choose to be 1 at this point. So Q has a range of 0 to 2 pi, okay? which we then said we're going to simplify because pi is a difficult number to work with. So we'll restrict Q to the range -1 less than Q less, I should say 0 less than Q less than 1, modulus of Q less than 1. So instead of pi, I'll make it 1. That's just a simplification. So that's the range of integration. This Q here is just dq. I won't keep writing that, but that's what it means. Okay. So this is the model. And this model came from this model for small q. So this is for q small. It's a good approximation. So we're going to take this model seriously, but it's equivalent to the original model only for small q. Okay, so this is the action we're going to work with. And we have to do all the steps. So we'll do the steps. So the first step is to integrate out the high frequencies. So in position space, what corresponds to a blocking which increases the length scale, in momentum space, that means you remove the high frequency components, frequencies that vary on a larger than the scale. So if your initial scale is this, you typically have frequencies that are of higher than that. Okay? But if your new scale is this, you only want wavelengths that are shorter than, that are longer than that. So all wavelengths between this and this have to be removed. Okay? So what we're going to do is we're going to split the thing into two ranges. So 0 less than q less than half, and half less than q less than 1. So all sigmas that have q in this range will be integrated out. So integrate these guys out. And so we'll introduce a notation. So we'll call it, what's the notation I've used? Actually here it's fairly trivial, so I won't even bother. So you can see that this action does not mix different Qs. It mixes Qs with the same modulus. Okay? So Qs in this range are independent of Qs in this range. So I can just write this sigma Q as for Q less than half plus and write this integration for one range and write the integration. So this is, sorry, I should write Q squared plus R here. I just write this action into two parts. This is the Q less than half, this is the Q greater than half. And there's no coupling between them. So the integration of these variables is trivial. It doesn't affect those at all. Okay. So the partition function remains exactly the same. So it's same except for some overall constant. And you're left with only these variables. So you just integrate that out, you'll get some constant factor, that is this constant, and then you're left with the remaining variables. So e to the power of, this is q now less than half, q squared plus r. That's what you get. So you can say d sigma q. So you're only integrating over the variables with q less than half. So this is end of step 1. And the whole point of choosing the Gaussian model is this is a trivial step, nothing to do. Minus sign, yeah. And a half. Okay. So this step will be more complicated when if you had quartic terms, because then all the frequencies would mix and you'd get modified. So that step is eliminated. So what is step 2? So you do some rescalings. Okay. So what's the purpose of rescaling? The purpose of rescaling is that you want your action to look exactly like the same as the original action, except for some differences in the parameters. This action doesn't look the same because the range of integration is different. Okay. So we want to bring it back to the same range. So rescale, so we'll call q prime as 2q. Okay, so you use q prime as the labels now. So when q goes from 0 to half, which is what it does, this q prime will go from 0 to 1, which is the original range. And then we'll use prime variables sigma prime q prime instead of sigma q, and they're related by some rescaling now, which, what is my, yeah. So zeta, some rescaling. We don't know what this value is, but we'll choose it in such a way that the action looks the same. Okay? It might turn out to be 1, it might turn out to be something else, but we'll just leave it up. So this is this is 2q actually. So sigma prime. Okay. So notice that we haven't done anything. All we're just saying, let's change the label on the variable. So if you had a variable sigma 0.5, it will now be called sigma prime with 1. If you have sigma 0.3, that will now be called sigma prime 0.6. And then there'll be a label. So we'll do this. So what does it physically correspond to? What it means is here the lattice spacing is L0. Here it's 2L0. So what this means is we are again going to, now that the lattice spacing is 2L0, all distances will be measured in these units rather than those units. Okay? So if you had a distance of 100 L0, in these units it will become 50 times 2L0. So in units of 2L0, the distance will be 50, not 100. So as your distances become smaller, the momentum label becomes larger. In other words, the momentum cutoff here is, say, 1 by L0 or 2 pi by L0. Here it's 1 by 2L0. So in units of this momentum, your momentum value will be larger. So what was 0.5 previously will, in these units, will be 1 in these units. So that's what this labeling is doing. And correspondingly, we allow for a rescaling of the variable of integration. Okay, so let's do that. So I'll just substitute everything. And now you have to remember that there is in this a ddq. So we'll replace that by ddq prime, which will bring a factor of 2 to the power of d. Okay. So what happens is that your new Hamiltonian becomes minus half c squared 2 to the power of minus d. Now it's q prime, where the range of q prime is 0 less than 1. And then it becomes q prime squared by 4 plus r sigma prime q prime sigma prime minus q prime. Okay. So I've just made this substitution. That's what you get. So as I said, this t to the power minus d because you change the region of integration, the variable of integration from ddq prime, whereas previously it was ddq. So that gives you d factors of 2, gives you a factor of 2 to the power of minus d. Okay, now is this, so you have to see, is this the same form as that? The answer is it's not because of this 1/4. Okay, so you have some freedom. That's what the freedom of rescaling was. So we'll rescale, we choose this parameter zeta, scaling parameter, to make this again 1. So choose, this is a crucial step. This letter is zeta squared 2 to the power of minus d equals 4. Okay? Or equals. So just solving for zeta. And then this becomes, so then this becomes minus half q prime with the correct range, q prime squared plus 4r. Okay? And we'll call this guy r prime. So now we've done what we promised to do. Namely, we've got a new Hamiltonian which calls it h prime, which is obtained from the earlier Hamiltonian. Exactly the same form, except that its parameter, which is r there, is now r prime and it's 4r. Okay, so all the rg, what the net effect of all this rg is this transformation. This is the iteration. Okay?
Up to some additional constants that you can add. So you're dropping some.
Well, there's a overall, when you do the partition function, there's some constant when you integrate it out. If you want, it's like a cosmological 0-point energy. Yeah, so because you're not worried about overall normal constants here, because you always take ratios. So whenever you calculate expectation values of spins, you'll get sigma q1, sigma q2. So this will be calculated by writing sigma q, sigma q1, sigma q2 times e to the power of minus beta h divided by, so this will, the same constant will occur in both of them, so it will cancel out. So it won't affect these correlations. So that's why we are dropping this constant here. This constant came from integrating out the higher modes. Okay, so now we just have to work out the consequences of this. Okay. So the first thing you can work out is, well, so if you calculate this sigma q1, remember the way we defined this was called this is how the gamma was defined. So this will now become calculated in the new theory. So we'll call this, so this will be okay. So if you compare the zeta, yeah. Great. Oh, actually, yeah, so there's a delta of, right? So this will become c squared so this gamma in the old one and this gamma in the new one are related like that. They're equal. This equals that. Okay. Just follow through the, that's how they're related. So you can say that gamma q And we've calculated gamma cube. What was it? It was 1 over r. And we expect for this, it's 1 over r prime. Okay, that's what you should get. And what is this factor? So that's 4. So we should get 4. Okay. This is 4, right? So you get that r is r prime by 4, which is also what we got here. Somewhere I had written it down, right? Where is that? Ah, here. R prime is 4r, or r is r prime by 4. So that's the same thing. Okay? So this also gives r prime is 4r. This also implies the same thing, or it's the same effect. And what about the correlation in the, this is zeta. No, this is psi, whatever, xi. This is the correlation length we calculated last time for the original theory was 1 over root r. So now your correlation length xi prime will be 1 over root r prime. So it's always the same formula. You have the same form of the Hamiltonian, only r has become r prime, so all your equations will be the same. Okay, is this clear? Previously, remember this thing gave you, we calculated the correlation length. Remember the formula for calculating the correlation length? We calculated how the 2-point function falls off, and we said this, so the form e to the power of minus r by xi, and this xi is square root of 1 over square root of r. Okay? So the same thing will happen here. It will be 1 over square root of r prime. And r prime is 4r, so this is 1 over 2. Now this is not surprising. Why is it not surprising? This is this is because the physical correlation length is not changing. It's the same system. The physical correlation length is the same. So if your correlation length was 100 times L naught in units of L naught, your correlation length is 50 times this unit, which is 2 L naught. So your new correlation length in units of the new lattice spacing is exactly half of the old one. So this fact that C prime is half of C has to come out no matter how complicated the Hamiltonian, because it just comes from dimensional analysis. It just says the correlation length is the same, it's the same system, and your units have changed by a factor of 2, so it has to become half. So this is a consistency check. So this had to come out. The other things depend on the details of the calculation, but this had to come out.
But that's because of our choice of this zeta square with the magnitude of 4. If we had chosen something else, then
No. Why did we choose this? We chose this because we wanted the same form of the Hamiltonian. If you had chosen something else, then the connection between C prime and R prime would not be this. Why did I write this down? Because I said I can use my old calculation, and the Hamiltonian is the same thing except R has become R prime, so I wrote down this formula. If you don't do that rescaling, then this formula will change. Okay? So this is a matter of convenience here. I did it to make everything standard form, except R has become R prime. So I can use all my old equations, all formulae, and calculate. That's how I got this. And then, but as I said, this has to be equal to that. This is just a check that you've done it right. So this has to be true. Now, maybe it's obvious to you, but can you see why R prime became 4R? Where did this factor 4 come from? See, R prime became 4R simply because of this 4, and we rescale it to 1. Where did this 4 come from? Basically came from the fact that Q was q prime by 2. Why did it become 4? Because it's the second power. So it's just dimensional analysis. The fact that R has a dimension of momentum squared is what brought that, the fact that it's squared is the fact that it brought this factor of 4. There is the 4. Yeah, this one. So it's just dimensional analysis. So in this particular case, R prime is obtained from R by dimensional analysis. Why? Because it's a free theory. There's nothing happening. Everything is fixed by dimensional analysis. So this is also the statement. Remember, in field theory, R is like the mass squared of your scalar field. So all you're saying is I change my lattice units to half of what it was. Then the mass as measured in those lattice units has to become twice. So the m squared has to become 4 times. That's all. So all this elaborate thing is just dimensional analysis. And all you've done is your u variables, your unit of momentum is measured in has changed by a factor of 2. It has become smaller because the lattice cutoff is smaller in momentum space. So all your dimensionful units, quantities, the dimensionless values will become scaled by that factor of 2 or whatever power of 2. That's all that's happened here. Okay? So when people tell you that the so-called fine-tuning problem, what is the fine-tuning problem you have in particle physics? It's that scalar fields are naturally heavy. What does it mean? You start with some bare theory with some mass, measured in low energy units, that mass has to be huge, simply because your units are small, that's all. So that's the fine-tuning problem, and you have to explain why scalars are massless, is explaining why this is a small number, whereas, as you can see, each iteration is going to become bigger. So R prime is 4R, you do it again, R double prime will be 16R. So it'll keep increasing, purely dimensional reasons. And so if you want a small mass now, your initial R has to be so small, that's called fine-tuning. Okay? And you can also see one more thing. When is C infinite? When R is 0. Okay, so that's the critical value for R. Okay. So in Kadanov's language, there the scaling was for k prime to k. Here it's r prime to r. So what is the connection between r and k? I think I wrote it down last time. But in the original variables, this r is actually, remember our original variables had the parameter k from the Ising model. And then we introduced this b. See, I wrote down, the model we started this was this thing, half k sigma n I. I wrote it like this, Sn plus I minus half b. So this is the model that in the momentum space became this. Okay. So R is related to, I did this last time, R is related to all this by this relation, b by k minus 2d. Okay. So in this model, instead of k, we are using r as a parameter. And the critical value of r is 0, precisely 0. So that gives you a critical value of k, which is basically, what is this, b by 2d. So kc. So r equals rc, critical value 0, implies kc is this critical value. Okay? So it's not, in units of k, it's not 0. Okay, but now we can use Kadanov's scaling argument. Remember the rule was r prime equals fr, and he's blocking, the blocking function is this. And from this we got a critical exponent. So r prime equals 4r, so fr is just 4r. Okay? Remember that we did this for k. We said k prime is f of k, and then we tried k prime equals 2k, and we got an absurd result that k has to be 0. And then we modified it. But here it's not an absurd result. 0 is the value, and this is the is precisely the values, and its critical value means R has to be either 0 or infinity. So fixed point, or I should say fixed point, implies RC equals 4 RC. That's the condition for the fixed point. So either it's 0 or infinite. So RC equals 0 or RC equals infinite. 0 is the critical theory that we are interested in, where C becomes infinite. Infinity means all your fields are infinitely heavy, essentially, in this language. You're so far away from criticality that there's no low energy dynamics at all. So this is not interesting. Okay? So if you go into that region, that theory has essentially no low energy behavior. You won't see anything interesting. So this is the kind of behavior that you're interested in. Okay. Now you can also do one more thing. You can use that formula. Remember we had a formula that said if Fk is Fkc plus lambda times k minus kc, we had a Taylor expansion. Then the critical exponent nu was log 2, what was it? Log 2 by log lambda, where this is the behavior of C as, in this case, it is k minus kc. So in our case, it's r minus rc to the power. So in our case, C is r minus rc, and rc is just 0. Okay, so this is r to the power of minus nu, but we know the answer without doing all this. It's just what is it? It's root. C is square root of r, so it's half, which is what you get here also. So if you put this as log 2 by log 4, which is half. Right? Lambda is 4 because this power is 4. R minus RC is 4 times. R prime is 4R. So this is the lambda. Okay, R prime is 4R. This is R prime minus R minus RC. RC is just 0, so it's just 4. So it's half. So you get out the critical exponent, and through this complicated analysis, you get a critical exponent of half, which is what mean field theory also gave you long back. Mean field theory means you assume some potential for the Hamiltonian, for the action, and just minimize it in terms of the magnetization. Then you can calculate correlation lengths. And you get the same value. And the reason you get the same as the mean field value is because there are no interactions. When you have a free theory, it's not doing anything interesting. It just gives you mean field values. Okay. So let me see if there's anything I have to say. So I'll just summarize in one line. Well, I'll just write down. So the summary, I'll just write it down here so that you know what to. So the first point is, this is always true. And I said this comes from dimensional analysis. The second point in this particular model, R prime comes out to be 4R. We did that, this came out of a detailed analysis here, but this is, in the case of mean field theory, this is also just dimensional analysis. So in the Gaussian model, this came from dimensional analysis, because R has a dimensions of momentum squared. And the third point is this is true. This relation is true, and more generally, if this is some function of let's use what have I used. More generally, so this came out trivially true because our analysis was very simple. Yes? This one. No. This half is because we did a blocking by a factor of 2. So this half came because blocking was by a factor of 2 in length. So all your length units change by a factor of 2. That's why if you blocked by a factor of 3, this would have been 1/3. Yeah. So, but other than that, it doesn't depend on any dynamics of the model. This does depend on the dynamics of the model, but because in the Gaussian model it's trivial, it comes out of dimensional analysis again. And finally, this relation, of course, depends on the dynamics of the model. Again, in the Gaussian model, this comes out trivially. But the fact that this relation and this relation are the same in general is true because your Hamiltonian has the same form. Okay? So this, in a general case, there would be a more complicated relation between C and R, but that relationship would be the same even after your after the rescaling. Okay. So that concludes the Gaussian model. Any questions about all this? So I hope the steps are very clear. The main 2 steps are this and this. And for those of you who are familiar with all this thing where you make this coefficient of q squared 1, this is the so-called wave function renormalization that you do in field theory. Okay. So in field theory, we always choose a renormalization z as multiplied so that the kinetic term has the standard form with half dm phi dm phi. This is precisely that rescaling. In this case, again, it's very trivial, but in a more interacting, complicated case, this factor will be more, will in general depend on the coupling constants and so on. Oh, it does. Because when you, in this case it didn't, but in the interacting case it will definitely depend because you will be doing integrals. And the integral value of the integral will depend on what dimension you're in. So 2-dimensional models will behave differently from 3-dimensional, 4-dimensional, they all behave differently. Free cases, everything is just dimensional analysis, yeah. Okay, so now let's go to the first, the non-trivial model, which is all the physics, which is the, change sheets, which is the 5/4 or the 4 spin. So let me erase this. So what I'll do is I'll erase this part. So I'll just add to this a quartic term. U times, and we're doing it in momentum space, so there'll be 4 sigmas, Q1, Q2, Q3. This is the simplest. So this comes from the adding the S4th term in momentum space with some parameter U. So this is the 3 independent momenta, and this is minus that for momentum conservation. Okay. And your partition function is Z is, so this is my H of sigma. So this is called, you can call this the free part, H sub F, and this you can call the interacting part, H sub I. Okay. Okay, so now, first step, so what we want is to get a new R prime and a U prime from R and U by doing those 2 steps. So the first step is to integrate out step 1. So repeat, integrate out sigma q with a half less than q less than 1. Okay. But this step is non-trivial, so I'll have to give names for the variables. So we'll let sigma 0 be the sigma q with 0 less than q less than half, and sigma 1, so we'll call this sigma 1, sigma 0 q, and sigma 1 q will be sigma q with q in that range. So my sigma q's I'll split into two labels. So these are the low frequency ones, these are the high frequency ones. So I have to integrate the sigma 1 out of the theory. Okay? So this, sorry?
You could have written a cubic.
Yeah, in general there could be a cubic term also. So this is for simplicity, you can invoke some symmetry, say you want only even powers. But in principle you could. It will change the behavior quite a bit actually. So I'll split this into d sigma 0, d sigma 1. So we'll write this as hf sigma So we'll write this sigma as sigma 0 plus sigma 1 and expand it out. Okay? So we'll write sigma q is sigma 0 q plus sigma 1 q. So here it's very clear what this means, because when q is less than half, it's just that, and when q is greater than half, it's just that, because these variables are defined only for that range of q. So this is called a sharp cutoff. So this is called a sharp cutoff, and we are doing that here for convenience. But in general, sharp cutoffs are not good things to do. You should do a gradual tapering down of momenta. You shouldn't split it very sharply like that. Okay, so we'll see that later on. But conceptually, this is the simplest. Okay, so we have to break this up. So HF this is our old term, so this is just HF sigma naught plus HF. Because it separates nicely, there's no coupling between sigma naught and sigma 1. This is a free case we've done already. But this guy has a lot of terms. Yeah. This is, when I wrote down a model, I wrote down B Sm squared minus U Sm fourth. So that's the fourth power of Sm instead of quadratic. And just is written in momentum space, it's that. So in position space is just 5/4 theory. Yeah, self-interaction, yes. I don't know what you mean by self-interaction. At the same point. These are at the same point, yes. Okay, so we have to repeat these steps for this case. So what we're going to do, okay, so let me just go over the redefinitions.
Here you had a non-trivial relation between B and R.
B and R, yes. Yes.
Is this U the same as that in terms of S variable, or is there a?
In terms of the S variables, this came from the quadratic part and the hopping part, Sn plus 1. Both of them contributed to this. This one comes from that.
No, that I'm asking, suppose I have that particular term minus U Sm to the 4 and use that change of variable to sigma q.
Ah.
Would I not get
You're worried about the precise factors. No, I'm not worrying about, I haven't, yeah. This is, you call it that. Generically, a fourth power will be some, you start with the initial model, you'll get some power here, but I'm just calling the whole thing U. It will be some quartic in the sigmas. See, this is just simple Fourier transform. So a product of 4 sigmas will go into 4 sigmas Q's with the convolution of all the spins, or all the momenta. Okay, so you just take this Sm to the power of 4 and replace each Sm by this. So you write inverse this, write Sm as sum over Q e to the y Q sigma Q, plug it into that, and generically you'll get 4 sigmas, and the momenta have to add up to 0, so you'll get a interaction like this. So the precise coefficient here, there may be some factors of 2 pi and all, I'm not worried about. In fact, I don't think there'll be any 2 pi. There may be, yeah. And of course, each of these Q's we are assuming is, this Q is just d Q1 by 2 pi d. Each integral is like that.
Still in your algorithm, all not Q less than.
Yes. So, yes. Good. Thanks. So that's why we are splitting it up now into 2. And as I said, the free term breaks up in a simple way like that. But the interacting term, which has 4, when you break it up, you'll get many terms. Okay? But before we do that, let's just define our, after you've done this integral, so you do this integral, what are you going to get? What is your final thing going to be? You're going to get d sigma naught q e to the power of minus some modified h of what? It's only sigma naught because sigma 1s have been integrated out. So after you've done this integral, so you do the sigma 1 integral, and you don't do the sigma 0 integral, you'll be left with something which you can write in that form. And our aim will be to calculate this. Okay? So typically, this will start out with a term like we had for the Gaussian model, which will be just that. And then there'll be a modified quartic term. So h prime of, what is h prime of sigma naught? Okay, so generically, it'll be the same type. It'll be of the form, just schematically, it'll be of the form q squared plus some r plus some u, I call it r prime, some u where now each of these integrals are from 0 less than half plus more. Okay. What is this more? This more could involve higher powers of sigma. So you could have 6 sigmas, 8 sigmas, and so on. So you could have 6 sigma naughts, 8 sigma naughts. 5 won't be there because you have the symmetry, but all the odd, all even ones will be there. Okay. And later on, we'll argue that these ones are not important for our purposes. So our aim will be to calculate the new r prime and the new u prime. Okay. But before we do that, we have to go through these steps. Namely, there'll be a rescaling. Okay. So the original variable was sigma naught, which was this one. We won't work with this sigma naught, but we'll work with the rescale sigma naught. So step 1 was to, after you've done this integral, we also have to rescale. So let's define what our variables are and then do the calculation. So we'll define as before. So q prime will be 2q. That's fixed because blocking by a factor of 2. And then you define sigma prime q prime times zeta as sigma naught q. Same step as before. In general, this zeta will not be the same as the zeta for the Gaussian model. We'll have to determine it afresh. And again, so here 0 less than q prime less than 1, 0 less than q less than half. So our q prime again is rescaled from 0 to 1. And we'll have to write, so we'll have to write this, whatever we get in terms of sigma naught, we'll write it in terms of the new variables. Okay. And I should point out that this relation will continue to be true, namely gamma q will be the zeta squared 2 to the power of minus d. This relation we had just followed from the definition of the 2-point function. This will continue to be true. Only this number could be different. Okay? This one will also continue to be true. So this also continues to be true, this also continues to be true. That has to come out. Okay, so what I'm going to do now is to expand the original theory. Okay, so we get so first of all, this is 1 minus hi plus and what we have to do is to do this integral d sigma 1 e to the power of minus hf sigma 1 Okay, remember we have to integrate this. This is supposed to go inside that. I expand it like this and write it like that. And I have to calculate these term by term. So the first one is just going to give me a number, the 1. This is going to give me some number. The non-trivial things begin with that and that. Okay, so we have to now evaluate that. And what is the basic rule? The kinetic term, hf, what is hf sigma 1? It's half q squared plus r sigma 1 q sigma 1 minus q. Okay. Because remember the free part just breaks up and it's just the original 1. So this is always there, doesn't do anything, it just comes along for the ride. All the non-trivial integral is done with this as your weight, so we have to do that integral. And what is the, so now you do this using contractions, usual Feynman diagram method. So these are just Gaussian, this is a Gaussian in sigma and these are various powers of sigma. So you're doing Gaussian integrals with various sigmas at the bottom and you use the basic rule that sigma 1q with sigma 2q, if you contract, you get this is the what does this mean? This means these are the Wick contractions. So I'm assuming you know basics of field theory, where if you have a Gaussian integral like this with various sigmas, this will have various numbers of sigmas in them. So you, in pairs, you take sigmas in pairs and contract them using this, replace them with this. So this is just a propagator for sigma. So in Feynman diagram, this is just a line with momentum q1. Okay. So then there's some combinatorics we have to work out. So let's look at the diagrammatics of this.
You mean sigma q1 and sigma q2, right? There is only one sigma. You mean sigma q1, sigma q2.
Ah, yeah, I should mean, yes, right. Yeah, this one refers to the high momentum variable. Good. Okay. Okay, so what are the vertices you have? So now let's work out the vertices. So we have 4 sigmas. So schematically, this is your vertex, sigma to the power of 4. Okay? So you have sigma to the power of 4. So you get sigma naught plus sigma 1 to the power of 4. So this will be sigma naught to the power of 4 plus various powers of 4c1, which is 4, sigma naught cubed, sigma 1 plus 6, sigma naught squared, sigma 1 squared, plus 4, sigma naught, sigma 1 cubed, plus sigma 1 fourth. Okay. For our purposes, the important ones will be this vertex, and this one will give the main contributions. Okay. So what are the vertices? So actually, what you're going to get, if in the first power, hi, when you put one of these, you will be doing integrals. You will be doing integrals d sigma 1 e to the power of minus h f sigma 1 with all these. Okay. Is this clear? This is your leading term in h1, the interacting part is sigma 4th. We'll have all these terms. So all these guys will go into that first term that you have to evaluate. So when you do the sigma 1 integral, this will just give a constant. What happens to this one? So you have d sigma 1 times, this is a constant, times sigma 1 times the Gaussian. So this is just q squared plus r sigma 1 q minus q. So when you do the Gaussian integral with sigma 1, with the sigma 1, what will you get? You'll get 0. So this will give you 0 just by symmetry. This will give you 0 again by symmetry. So you'll get something non-trivial from this one and this one. Okay? And you just calculate that using combinatorics. So this is sigma 1 squared. So you have 2 sigma. So you just contract. So you can think of this as sigma naught, sigma 1, contract it with that propagator. And there will be a coefficient of 6 because there are six such terms. What about this one? This one, when you do the integral, you'll get, so all of them are sigma 1s. So you'll contract them in pairs like that and like that. Okay. So you're ending up calculating this and that. How many of these are going to be there? So you have one term with sigma 1, 4. How many such diagrams will there be? Well, the simplest way to see that is you just take one of them and you can connect it to any 3 of those. Okay, so there'll be a factor of 3. So let's say you connect it to this one, and then you connect the remaining one. So basically there'll be 3 such diagrams. depending on how you contract it. Okay? So there's a factor of 3 into that contraction. And this, of course, there are 6 of them. Okay? So this is first order in U. So that's the first term there. Okay? Now let's look at the second order diagrams. So what I'm going to do now is just do some combinatorics for you, and then I'll write down the answer, and you'll see where the terms come from. Okay, second order diagrams, there are diagrams like this. That's one diagram. Then there are diagrams like this. Okay. Then there are diagrams like this. So what do I mean by diagrams like this? So what's happening here? Remember, after you've done the integration, which is over the sigma 1s, what is left are sigma 0s. So these are the variables that are left behind, and these are sigma 1s that you've integrated out. Okay, so here there's sigma 0, sigma 0, sigma 0, sigma 0, sigma 0. This is sigma 1. Actually, this is sigma 1. This is the vertex. Sigma 1 integral. This is just the leg. This is a sigma 1 integral also. Okay. Here also, this is sigma 0, sigma 0, sigma 0. This is sigma 1. The internal lines are all sigma 1s because those are the ones you're integrating and replacing by those propagators. Right? Now I claim that this diagram has to give you 0.
That
Huh?
cannot be sigma.
Which one? This one. Why?
No, the other one. Sigma
This one.
No, the same diagram. You said that the internal line is sigma 1.
This one is sigma 1.
Sigma 1, sigma 2.
This is sigma 1 cubed sigma naught term. This one. So this is a sigma naught cubed sigma 1, sigma naught cubed sigma naught sigma 1 cubed. So you have to tell me why this diagram gives you 0. As an integral, it's not 0. I mean, this is a non-zero propagator, this is a non-zero propagator. But why is this 0? Because the internal momentum here is less than half because of sigma 0. Okay? This momentum goes through, but this sigma 1 has to have momentum greater than half. So you cannot have a sigma 1 with momentum less than half. So this diagram won't be there. So because of that, it will be 0. Otherwise, in general, it's there. So is this clear? Sigma 0s all have momentum less than half, and sigma 1s all have momentum greater than half. So this line is non-zero only if the momentum is greater than half.
Yeah, I was thinking they are different particles on both sides of the.
Okay. No, it's the same. So this sigma 0 has momentum less than half.
At least they are, they
Different frequency components. Yeah. So this will be 0 because of that, for that reason. Okay. This loop is non-zero. Again here, for the same reason, if the momenta of this plus this is less than half, then this diagram will not be there. But if the momenta add up, because of 3 of them now, so this could be 0.2, 0.2, 0.2. It can become 0.6. So then this diagram will be there. Okay? So it depends on what the external momentum is. But in general, this diagram will be there, and it will give you a vertex involving, in your Hamiltonian, involving 6 sigma naughts. Okay? So this will give you, this is the extra terms that I wrote down. Yeah, this will contribute to that. Okay. Okay, so now I'm going to, what I have to do now is to work out the combinatorics expressions for each of these. Maybe I won't do that now, I'll be in a hurry. It's 12:30. Okay, so next time we just complete this program evaluate these diagrams, and get you H prime. Okay, so we'll stop here.